So I thought instead of just doing a screenshot and showing you the times of each op, that I'd quickly talk through it. So this was the part. It was done in 2 operations. So one side was done where it made all the holes and removed the majority of the material from around the outside from where it was a square block, and then it was flipped over and the rest of the material was removed and then it was faced off flat. So the first op was to do these 8 holes. They're 5.5mm holes for clearance for a M5 bolt. They go all the way through the stock, which was 12.5mm thick when I started. So my standard, it was a 1/8 bit. So the T8 tool, quickly, what I'll just say is, even though not the most efficient, e.g. you can see here on bore 9, that it's going all the way through the stock, but it actually doesn't. There's going to be a pocket there later, but it makes those holes all the way through so that I can get all the 1/8 bit tool operations out of the way in one go, so I don't have to keep changing tools over all the time. So the first operation was to bore these 8 holes. They're 5.5mm holes for clearance on a M5 bolt. They go all the way through the stock at 12.5mm. The chip load is 0.05. Hang on, let me bring that up just in case you're a visual person. The 12,000 RPM, everything's run at 12,000 RPM. Feed to 0.05mm, which gave a cutting feed rate of 600. A pitch of 0.3mm, which is 0.3mm of depth per time around the bore. I always do a finishing pass, which I do a 0.15mm step over, and then I do what is a spring pass, a repeat pass, which just cleans that edge up nicely. And as you can see, that took 4 minutes 26. They could have probably been run faster, but I probably wouldn't have increased the pitch at all. But yeah, they could have been done faster. So these 4 holes, which even though they look like they're in a pocket, they're actually going all the way through the material because this pocket hasn't been machined yet. So again, this is a bore operation with a 1/8 bit, 12,000 RPM, 0.05mm chip load, which gives a feed rate of 600, and again a pitch of 0.3. These holes are 4.2mm in diameter, ready to be tapped for an M5 thread. A 1/8 bit is 3.175mm, so this bore movement is only a millimetre. This operation, even though it went through fine, probably could have done with being slowed down a little bit. So I could have either slowed down the cutting feed rate, or I could have slowed down the pitch. Just, it needed some of the load taken off, but it went through absolutely fine. It was just a little bit noisy. And then we come into this 2D adaptive, which cuts a slot all the way through the material. So this does a helix entry, which goes all the way through the stock and out the bottom. So you can just see that it clears out the bottom there. And then it does a 2D contour. No, not a 2D contour. It does a 2D adaptive to clear that pocket out. So again, this is 1/8 bit, 12,000 RPM. Obviously, I knew that this was going to be a 2D adaptive and it was going to be making its cuts at full depth on this workpiece, which was 12.5mm. So I actually lowered the feed per tooth to 0.04, so it was just having a little bit of a lighter workload, which gave a feed rate of 480mm per minute. Run an optimal load of 0.09, which is, again, I knew it was a deep pocket, but that is about the maximum that I'll run for a 1/8 bit anyway. After that, especially on long 1/8 bits, you're going to start breaking them. But yeah, so clearing that pocket out, including the helix. Hang on, let me give you details for the helix. So the helix entry was 1 degree ramp angle, which could have been more, 1 degree taper angle, which was fine, and a diameter small enough to make sure that it could helix down inside the pocket without hitting the sides that were going to be cleared out afterwards. So clearing that little pocket out took 7 minutes 38. Could it have been done quicker? Yes, probably, but it would have been at the risk of breaking the tool, because it was a 17mm flute length, 3.175mm or 1/8 bit. So it was sort of like one of the longer zero flute 1/8 bits that you can get, and I didn't really want to break it, to be honest. So I took it nice and easy. Tool 20, changing over to Tool 20. Tool 20 is a 6mm 3 flute offset helix end mill for aluminium, which is DLC coated, and this one, if I recall correctly, has 18mm flute, so more than enough to go all the way through this part without any problems. So this bore operation, again, we've still not machined this large square pocket, so this bore operation goes from top of stock all the way through to the bottom. 12,000 RPM, running a feed per tooth of 0.04, which is fairly low for this bit, which gave me a cut and feed rate of 1,440mm per minute. Ran a gentle pitch of 0.2, which was a gentle pitch, and finishing passes, and again a spring pass, a repeat pass. I could have run 0.3. My machine, well, generally it's quite a modified 3018 with extension and linear rails, etc. I can push my pitch on these almost to a millimetre. It's not happy about it. It will do 0.5 millimetre without complaining. But when you're doing what is sort of like a deep slotting operation, which a bore is, you want to slow it right down, because otherwise you get really high tool engagement and it builds the heat up, even with air and coolant on. So sometimes you just have to sacrifice just that little bit of time. But yeah, so that went through. It's going to recalculate everything. That went through in 4 minutes and 10 seconds. Then the counter bore to that bore, which is from top of surface to, if I remember rightly, 3mm below the contour, which is the top of that square pocket. So not very far at all. Obviously, I knew that the stock in the middle would have now dropped out, so we've only got tool engagement on one side. So we went for a feed per tooth of 0.05, which gave a cutting feed rate of 1800mm per minute. But again, I ran it at 0.2, finishing pass as I always do. I could have, again, run this pitch higher. I've only really just started using these larger 3 flute bits on one machine, and I'm still kind of feeling them out. But ultimately, I've got a perfect, nice clean hole that took 6 minutes, which isn't too bad, you know. On when the 3018 was original, that probably would have took an hour by itself. No entry, because the stock in the middle is already fallen out. So it's just doing this sort of counter bore circle, which is actually where the locating circle on the front of the NEMA 23 stepper is going to sit. We then come into this pocket clearing, which was done as a 2D adaptive. So we helixed in, we didn't helix in actually, because obviously this is a big hole. So I picked this pre-drill position, which is the center of the bore that had already been cleared out. I dropped it to the maximum height, but with a stock to leave of 0.15mm. So the bit would have dropped to just above this plane that this circle is on, and then started doing the adaptive, you can see here. So again, this was 12,000 RPM. The feed per tooth actually calculated by Fusion was 0.0596, which I ran it at, with a cutting feed rate of 2,150. Yeah, again, This was the recommended chip load and speed for the bit based on the RPM. Yes, it seems quite high, but you can tell by the results it works absolutely fine. So I took an optimal load of 0.15. My machine will take an optimal load of roughly 0.2 with this bit. Any higher than that, and the 500 watt spindle isn't powerful enough. It will just stop the spindle on cuts. It's not a rigidity issue, it's a power issue. So I'm limited to 0.2. If I want to have a little bit of leeway, I run it at 0.15. So we had the stock to leave of 0.15. And that is that one. So that took a total of, I was going to recalculate it, but that took a total of 9 minutes and 6 seconds to clear out that pocket using an adaptive. Again, that was a 6mm free flute bit. We then cleaned up that pocket. So all we were taking off was essentially the 0.15mm stock to leave that was left from the adaptive, both axially and radially. So that took a whopping 29 seconds. And again, we ran that at 0.05, 1800mm per minute. We just flew around that. So yeah, 29 seconds. Now, this here looks massive at 19 minutes, 0.37 seconds. But what this actually done, and I could have saved quite a bit of time here, but the workpiece was held in a vise. Obviously, I don't want to cut my vise, so a 2D contour to cut straight through was out of the question. I could have done a 2D contour with tabs, but then I wouldn't have got the edge finish that I wanted, because I would have had to have then cut the tabs off and sanded it down and tried to repolish them, and I wanted nice machined edges. So cutting it like this, it leaves a hat on the part. So you can see there, if I recall correctly, I left a 4mm hat on the part. But yeah, so again, that was a 2D adaptive. It cleared off all that material from that square into this edge, and it took 19 minutes. I think if I were to do it again, because it will become clear in a minute why, and the 2D chamfers in the end, I didn't actually run them. I just left it with square edges and run a deburring tool around it. So what I would probably do next time is create a fixture of some variety to hold the entire workpiece up away from the vise, so that I could go all the way around the edges in one go. The only reason that I didn't do that is because I had plans to run a chamfer around all the edges, but in the end I didn't bother doing that, so I cost myself a load of time by setting up the cam in a way that the part was there and could be have a chamfer around the edge, but I didn't do it in the end, purely because I don't need smart chamfers around my parts, to be honest. You know, they're not production parts, they're parts for me. So that was setup 1. Setup 2, which is 5, 6, 7, 8, 9.5 minutes, was making a fixture block for when I turned it over, and it was just a square block that bolted into these holes and allowed me to clamp that in the vise when it was turned over. So now we've turned over, let me just close that off, show you the stock. So the stock itself has got a hat on, you know, which is left over from the last operation, the last 2D adaptive on this part there. So that 2D adaptive, obviously left this pocket around the bottom. So when we came into here, we now had, and flipped the part over, we now had the pocket around the top. So because of the way that a 2D adaptive works, it's going to take exactly the same amount of time on one side as it does on the other side, because it's working on a feed speed and a radial chip load. So the amount of material that you're removing in depth doesn't change the cut time. It's the amount of material that you're moving radially that changes the cut time. So if I thought about it and fixtured better on this first operation, I could have cut all the way through on that first adaptive and saved myself 19 minutes by running this second adaptive, because it wouldn't have even needed it. But it's not a production part, it's not time critical. So anyway, we just ran the second adaptive, which is the same as this one. So just in case you want to have another look at it again, so it's 0.0596 millimeters per minute, which gave a feed rate of 21,050 millimeters per minute. The optimal load of 0.15. And again, didn't need helix entry. I plotted the entry off to one side, if I remember rightly for this one. Thanks for that. Yeah, so you can see my entry is here, off to one side of the part. So no helix entry needed. I plunged down outside of the stock and then just let the 2D adaptive work its way around. On this second 2D adaptive, there was no stock to leave, so it just went through really quickly and was then done. And then I just faced this side. But even though I have the face set up in CAM to take 2 minutes 39, I have preset macros in Universal G-code sender for facing off parts, and I also have custom handwritten G-code where I can just easily go in, put the part size, and it will just face it off. So in the end, I actually face this off at 2,500 millimeters per minute, 12,000 RPM, with a 40 millimeter 4-flute surfacing bit, and it probably done it in around 10 passes in roughly under a minute. So yeah, I thought this would just be a bit different, better than just me posting it took this long. So let's have a quick look. So bearing in mind that obviously we lost that extra time with the adaptives, and there's a few minutes in there. Let's have a look at, so setup 1 machining time was 56 minutes and 49 seconds. Setup 3 machining time was 26 minutes. So it took an hour and 20 minutes machining time, plus the setup time, probably say 2 hours in total, starting from a rough aluminium block to a completed part. But again, I could have knocked that down. I could have lost the second adaptive by changing the work holding. I didn't do this facing at 2 minutes. This 2D adaptive here, I could have either run that as a 2D adaptive, or if I'd say machined these holes first and then bolted something onto it to raise it up out of the vise so that I could cut all the way through. I could have done a 2D contour that went all the way around it and cut it through. It would have given me a few options. It probably would have got it under an hour. You know, if I'd sped these bores up, this 2D adaptive I took really carefully, that could have been done quicker. That bore could have been done quicker. That bore could have been done quicker. I tend to run fairly safely. This 2D adaptive was probably about bang on for time, to be fair. Cleared a lot of material out, took 9 minutes. Pocketed and then adaptive. Anyway, I'm rambling on now. I just thought it would be something different to do a little video of how I cammed this part and the times that it took, instead of just posting a screenshot.